Muy buenas tardes a todos, otra vez en un día de conferencias de la Asociación Geológica Argentina. Hoy tenemos el placer de una conferencia organizada por la ComPetro, que ustedes saben que es la Comisión de Petrología, Ígnea y Metamórfica de la AGA, ComPetro como le decimos todos, y para hacer esta presentación tenemos a la doctora Florencia Gargiulo. Muchas gracias a Florencia que está en esto y a la doctora Larissa. Florencia, por favor.
Bueno, buenas tardes a todos, bienvenidos a este ciclo de charlas organizada por la ComPetro. Yo voy a presentar a la doctora Larissa Dobrzhinetskaya, quien es doctora en Geología y Mineralogía y es catedrática del Departamento de Ciencias de la Tierra y Planetarias de la Universidad de California en Riverside, California, Estados Unidos, desde el año 2001. En el año 2015 fue nombrada profesora emérita y ha dictado numerosos cursos de grado y posgrado en Estados Unidos y universidades de China, Japón y Rusia. Ha dado numerosas conferencias especializadas en diferentes eventos científicos internacionales. Sus intereses científicos están relacionados con estudios mineralógicos y petrológicos en rocas naturales de ultra alta presión, en física mineral, geología, síntesis mineral en laboratorio, para entender el movimiento de las placas tectónicas y la construcción de montañas a través de los procesos que operan en el interior terrestre. Sus estudios innovadores en el campo y el laboratorio condujeron en el año 1995 al descubrimiento de microdiamantes en rocas con afinidad cortical, en la región de los Neises del Oeste en Noruega. Inició estudios de microdiamantes y de los minerales y las inclusiones fluidas asociadas a estos minerales en nanoescala, utilizando microscopios electrónicos de barrido y transmisión y técnicas innovadoras como Focus Ion Beam y NanoSIMS, espectroscopía infrarroja y Raman con soporte de sintotrón. Ha recibido más de 15 premios y distinciones internacionales. Es beneficiaria de una beca de largo plazo de la Sociedad Japonesa para la Promoción de la Ciencia y el Consejo de Investigación de Noruega. Ha sido elegida Fellow de la Mineralogical Society of America, Fellow de la Geological Society of America, entre otras, y se desempeñó como presidenta del grupo de trabajo en el Programa Internacional de la Litósfera, que une a geólogos de más de 32 países del mundo. También fue vicepresidenta del Grupo de Trabajo Equilibrio en Minerales de la Asociación Mineralógica Internacional. Organizó y convocó decenas de sesiones en reuniones de la American Geophysical Union, en reuniones de la Geological Society of America, conferencias Goldschmidt y muchos otros foros internacionales. Ha publicado más de 150 trabajos en revistas científicas internacionales y 2 monografías en el CEDIA. Es editora científica de la revista Physics and Chemistry of Minerals desde 2015 y es miembro del consejo editorial del Journal of Metamorphic Geology desde 2012, del Journal of Earth Science desde 2008 y del Open Mineralogy Journal desde el 2006. Para mí es un gran honor entonces tener a Larissa en este ciclo de charlas organizadas por la ComPetro. Le doy la bienvenida en nombre de la ComPetro y de toda la comunidad geológica argentina y de los distintos países de Latinoamérica que estén conectados hoy para escuchar su charla, y espero que todos puedan disfrutar del conocimiento que ella tiene para transmitirnos en la charla de hoy. So Larissa, you feel free to start with your presentation whenever you want.
Okay, good afternoon. Thank you very much, Florencia, for your introduction. Even I don't understand Spanish language, I felt that you ran through my biography and my citations and my participations in different conferences. So thank you very much for your great introduction. This is my pleasure to give talk today about small diamonds and how these diamonds affect to the development of the big geological concepts. I am Larissa Dobrzhinetskaya, Department of Earth and Planetary Science, University of California at Riverside. So, diamond is a very simple form of carbon. And if you look at the periodic table, carbon belongs to non-metallic group. It's standing out between boron and nitrogen. The nucleus of carbon consists of 6 protons and 6 neutrons. You see red and the black color here. And they also 6 electrons to balance them. And we have 2 electrons on the K shell and 4 electrons on the M shell. We know also that carbon is the 4th most abundant element in the universe. All living organisms and vegetation on the Earth contain significant amount of carbon. So we know that source of carbon on the Earth's surface unlimited. So then we have to learn how this carbon going down inside of the Earth and diamonds are formed there. For centuries, diamond is known as a subject of admiration. Everybody knows that diamond is forever. However, not all public, general public knows that diamond is a great geological material and also has a significant industrial application. If you see this diamond, there is inclusion of there. Excuse me? Okay, everything is okay? I see somebody's voice. Okay. Can you please mute your microphone? So this inclusion of garnet, for example, is study will give a lot of information about geological conditions where diamond was formed. Industrial implication. We know diamond saw to cut rocks. We know abrasive powder to polish these rocks. And we know also that diamond can be a semiconductor if it docks with boron or other elements. So let's now speak about mineralogical form of carbon. The mineralogical form of carbon, minerals which consist only one element of carbon. It's a diamond, lonsdaleite, and graphite. Everybody knows diamond. We know this from our mineralogy course in the 2nd grade of the university. The diamond has a crystal, a cubic crystal symmetry. Cell dimension of the in the diamond structure is 3.56 angstrom. What does it mean? It means that each atom of carbon in cubic structure is situated on the same distance from each other. Diamond is inert. Diamond is very hot. This is hardest material which is known on the Earth, and also hardest material which is made in industry in laboratory. There is nothing harder than diamond yet created. So diamond usually can be found in kimberlitic pipes, in lamproitic pipes. Diamond is known now within metamorphic rocks formed during continent-continent collision. That's small diamonds, which we will be talking today about. Then they are solar diamonds, and they are meteorite or impact diamonds. So let's talk about lonsdaleite. Lonsdaleite, you see here, lonsdaleite from meteorite. Lonsdaleite, somebody says, is hexagonal diamond. Yes, it has a hexagonal symmetry with a distance between atoms in A direction 2.52 angstrom and in C direction 4.12 angstrom. However, in the last 5-10 years, there are a lot of material science papers which says that there is no specific mineral as a lonsdaleite, because lonsdaleite is the same diamond, only disordered structure. The structure is disordered by stacking faults, which can convert cubic symmetry to hexagonal. So lonsdaleite, at least, had been found within meteorite and in impactite rocks. Graphite. Everybody knows graphite. Graphite is can be found everywhere in sedimentary rock, in metamorphic rock, in igneous rocks. Graphite has a hexagonal crystal symmetry, and cell dimension 2.46 and 6.7 angstrom. So in this direction, in horizontal direction, according to the A-axis, the atoms are very close to each other. Why graphite is a very good electrical conductor, but in other direction between plane, we have a lot of space, and why graphite is very soft, and graphite is used for pencils. Okay, let's now talk about thermodynamic properties of the diamond. So everybody knows that reaction of graphite to diamond is very sluggish. It's very difficult to convert graphite to diamond. And also not easy to convert diamond to graphite. So why this has happened? Because of structural features. So, and structural features, package of atom, they provide us special enthalpy and entropy. Graphite has an enthalpy 0, whereas diamond has enthalpy 1.89. The entropy 5.7 for graphite, and very low, twice low for diamond. It says that thermodynamic properties will be different. Yes, it is. To convert graphite to diamond, you have to go through the huge energy barrier. You see here activation energy, huge, right? You cannot go directly from graphite to diamond. This is a reaction energy which require for diamond. But this is special energy which need to activate transition of graphite structure to diamond. Yes, it is. We're going from hexagonal structure, less organized atoms of carbon, to cubic structure, where all atoms should be in an equal distance from each other. So to go through this energy barrier, you need to add some catalyst. And you know that in experimental setup and in industrial laboratories where diamond can be produced from graphite, we need to add a lot of catalyst. Usually this is metals, which make additional energy and the reaction of graphite to diamond going faster. So to conclude, the structure of diamond and graphite very dissimilar. So their enthalpy and entropy as well dissimilar. So a specific energy barrier exists during graphite to diamond transformation. If you look at now in the right side of the slide, you see here the pressure temperature diagram of carbon, the temperature in Kelvin and pressure in GPa. The white field is a field where diamond is stable, and the yellow field where carbon exists only as a liquid carbon. It's very high temperature, more than 4,000 K. And the gray field is the stability field of graphite. And we see here the graphite can exist from low pressure and low temperature towards to higher pressure, about 12 GPa, the temperature 4,000 K. So here also you see the different colored field where diamond was synthesized from carbon-rich fluid and silica carbonate melt, and also the catalytic high pressure and high temperature diamond synthesis in industry, and also synthesis of diamond without catalyst. You see, if we don't have catalyst, we have to increase pressure and temperature significantly to convert graphite to diamond. And finally, you see metastable diamond. Metastable diamond produced in a specific technique, chemical vapor deposition. This is the line, red line, show the stability field of so-called production of metastable diamond. So now we're going to speak about these small diamonds. These diamonds were very unusual when they were first discovered. They were discovered in the 1980s by chance, as all mineralogical discoveries happen. It was discovered in Kazakhstan, in metamorphic rocks of continental affinities. This you see map of Kazakhstan, this Turkmenistan, Uzbekistan, Afghanistan is here to the south, China is here, and this is Russian Federation, just to understand where Kazakhstan is on the globe. So how it happened? So geologists were doing geological survey and were mapping this territory. And they were processing rocks, and they found in the heavy mineral fractions unusual minerals which appeared to be diamonds. But they were so small, only micron size. They have been visible only on the microscope. And practically nobody believed that this is real diamond. However, scientists took this diamond for evaluation, and yes, they confirmed this is diamond. So, unusual characteristic of this diamond, as you see here on this image, 5 micron size, 5 micron size. So only micron size. They occur in metamorphic rocks. In that time, they have been determined to be rocks of amphibolite and granulite facies. So low pressure and temperature not more than 800 or 700 K Celsius. So morphology was very unusual. Diamonds have been like a roses, dendritic crystal, cuboid, very rare cube, octahedron-like. So now I would like to show you how this diamond looking under the microscope. If you make a thin section and you suspect that maybe diamond should be there, how you can suspect? How this idea come to you? Okay, you know now that these diamonds were found in orogenic belts, in metamorphic rocks. You go to this place in your country or in any other continent and try to find diamond or any other ultra high pressure minerals. First, what you do, you collect samples, come to laboratory and do thin sections. You do polished thin section on the polished side, or you can do regular petrographic thin section. But if you're looking for diamond, never use diamond paste and diamond abrasives, because you can contaminate your sample. So this, for example, optic microscope image, transmitted light, regular, transparent petrographic thin section, 30 micron thickness. You see here garnet, transmitted light, cross nickel. You see here the garnet, okay? You see here phlogopite, and you see here chloride. And quartz, which we know now was after coesite, high pressure polymorph of quartz. And you see here at the grain boundary, there is something very round and non-transparent and actually isotropic, because diamond has a cubic structure. What is isotropic else in this mineralogical setup? Garnet, right? Garnet also isotropic. So you see something isotropic, then okay, it's probably diamond. Yes, this is diamond, but you have to confirm this diamond by different techniques, okay? So this diamond sitting on the grain boundaries. It's a very important observation, because then later it will help us to build a concept of the origin of this diamond. So this is another crystal of diamond. It's not very well seen. However, when I show these samples to students, I usually tell them, when you look at it in the microscope, you see the mountain. Diamonds usually, because it has a very high refractive index, look like a mountain. And here I show you similar sample in reflected light, the polished surface of the thin section. You see here diamond, 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 a lot of diamonds. There are 1, 2, 3, 4, 5 crystals, 4 crystals of diamond, all of them sitting inside of garnet. Sometimes you can find the same amount of small diamonds in zircon. Why? Because diamond likes to be in refractory minerals. Garnet and zircon, they protect this diamond from destruction. So now there were several diamond terrain discovered in the world, dozens, okay? Some of them very unconditionally, well confirmed that this is real diamond. Some of them still under discussion, new data come, new criticism come, but eventually we know in science, controversy is a good trigger for the truth. Here I show you the map, which we published in 2011, and you see here that diamond and coesite and other ultra-high pressure minerals are found now almost in all continents. Even in Antarctica, yeah, you have a coesite. So we have coesite in Greenland, we have diamond in West Greenland. We have a lot of diamond in European continent and in China, Kazakhstan. So in South and America, and also coesite was found in Brazil. Even there are a lot of kimberlitic diamonds in Brazil. There is a chance to find diamonds from ultra high pressure terrains in this continent as well. So why this discovery is important? The discovery of this diamond triggered a revision of the plate tectonic because it provides evidence that buoyant continental crust can be subducted to depth of more than 150 kilometers and then return back to the Earth's surface due to tectonic exhumation. And you see here some cartoon showing how it happened. You have here subduction zone, seafloor metamorphism, extension, and then you see here in the continent collision and ultra high pressure metamorphism, and potentially this rock may contain diamonds. So this is how diamonds look like in metamorphic rocks. They're very, very small and very unusual by their morphology. So I would like to show you more and stop on discussion of this, attract more your attention to the unusual morphology, because this is a very important observation. It will move ahead our understanding how diamond was formed. Okay, this is digital camera optic microscope image. Now we see zircons. What you do, it's very easy. You collected rocks in the field, then you crush them. And everybody knows how to separate zircons because almost all laboratories, they do zircon separation for decades because they use zircon for dating. So when you take the zircon grains and put them on epoxy and glue them on the petrographic thin section slide and then polish them, you can find a lot of diamonds in the zircon from ultra high pressure metamorphic terrain. So you see here diamonds again, two big crystals standing as the mountains on the flat surface of zircon. And this is scanning electron microscope image. You see here, this is this diamond, okay? So this is high magnification of the same diamond. You see details of the form. So again, another crystal, again diamonds here. And this is, we see 1, 2, 3, 4 crystals together. This is a polycrystalline diamond. Then smaller diamond crystals. And you see how well polished is the surface of zircon. Diamond still alive. Nothing happened to diamond because if diamond is not contamination, okay? If diamond is a real, indigenous, as we call it, real, it's mean primary, belong to this rock formation. So the diamond has a very, very strong connection to the surrounding mineral host. So, and you will see very well polished both minerals. So, okay. So now we're asking ourselves, what is inside of this diamond? Because to understand this unusual morphology, you need to learn what is inside of this diamond. And this exactly question, which I asked myself when I started to work with diamonds a decade ago. We even didn't know what kind of method to apply. However, your curiosity moves you ahead and extend your horizons to find a technology or instrument to study these diamonds. So the idea came easy. Diamond is chemically inert. So we have to find some inclusions inside of this diamond, because the inclusions will be pristine witnesses of the media from what diamond was crystallized. In that time, however, we didn't know very much technique available to study the small diamonds. And I remember I wrote several proposals to National Science Foundation, and they every time were denied during first 2-3 years, because there was no technique how to get inside of this diamond. Then eventually, when you're talking to colleagues, you go to different laboratories and you learn about all techniques, not only from geologists, but from material scientists, from physicists. Then I learned, actually, new instrument appeared, focus ion beam instrument. Then there were synchrotron facilities. They are not available in all countries, but they're available in the United States, in the Euro-Union, and they're available in Japan. So synchrotron-assisted X-ray and different spectroscopic facilities. If you will apply to these small diamonds regular Raman spectroscopy or regular infrared spectroscopy, you will not get good result, because the beam of that regular Raman is larger than diamond itself. So you cannot get a good result. So technologies came, and this is synchrotron-assisted X-ray and spectroscopic facilities assisted by synchrotron, focus ion beam instrument, which allow you to cut very, very thin sample, which we call foil, to be studied at high resolution scanning and transmission electron microscopy. So now I would like to stop on these techniques, because study of inclusions by this technique do not take a lot of time. It's usually hours, even sometimes minutes, especially with synchrotron radiation. However, preparation of samples and understanding what you're going to do with them takes months, a lot of time. So I prefer to explain my audience, to remind them what does it mean, this technique. So synchrotron studies of geological material. What is a synchrotron radiation? So there are several national synchrotron light sources in the United States. We contacted and used Brookhaven National Laboratory in the United States. So we visited these facilities, and in such facilities, usually they do not work very much for geological purpose. However, if scientists who study geological material express their interest, the local administration usually invite them to conduct that research. Now we have a special organization which allows users from geological environment come to the synchrotron facilities and study their samples. So let's now talk, what does it mean, synchrotron radiation? So you see that this is a very complicated technique. You have here X-ray ring, the source of X-ray radiation, some radioactive material which produce different rays, including X-rays, okay? So, and these X-rays, they are accelerating, they are moving along this ring. When a beam of electron reach the speed close to the light speed, it's bent out from their trajectory and get out with a different wavelength number. This is we call synchrotron radiation. And because it produces final beam getting out with different wavelength number, we can create, and they create different stations, okay? Here, one station, second station, third station, another station here, one station caught and apply the X-ray. Second, caught and apply wavelength number ray, which used for Raman spectroscopy. Another one for infrared spectroscopy, and many, many, many others. So we use synchrotron infrared spectroscopy in Brookhaven National Laboratory. And we brought there this little diamond from Erzgebirge Massiv, Germany. By that time, these diamonds were discovered in Erzgebirge by Hans Massoni, scientist from invited to the field, and we show our data, and so we got samples and we started to work ourselves. So this diamond have been selected from the rock by method of the thermochemical dissolution. And you see this diamond even deserves to be invited on the cover page of the PNAS journal, Proceeding of National Academy of Science, where our paper was published in 2007. So let's see here this synchrotron infrared spectroscopy. This is graph show here. This is wavelength number in centimeter -1, and this is absorbance. We see this graph. What we recognize here, this diamond contains stretching motion of H2O molecule. It's a OH group, OH region, all these small peaks. Then this is diamond absorption peaks, okay? Then we found here this specific peak about 1,300 centimeter -1 is a bending motion of H2 molecule. It means there is a molecular water there. Then we found CO3 radical, okay? There is a gas, CO3, okay? Some carbonate. So then we found nitrogen, and nitrogen have two peaks, the big and small peaks, and also two peaks in this distance. They show that they are silicate inclusions inside of this diamond. We conducted more experiments with synchrotron infrared spectroscopy on different diamonds, and this is another sample, again diamond from Erzgebirge. We see here stretching, again stretching OH region, again CH radicals, and then we see molecular water, we see CO3, nitrogen, and silicates. What is the result? I summarize. We found nitrogen. And there is a concept that we can recognize nitrogen defect. This concept was developed by Wayne Taylor, was published in 1999. And now we know that according to the nitrogen aggregation, diamond can be separated and recognized as a diamond from kimberlitic terrain, a diamond from ultra-high pressure terrain. So the diamond from ultra-high pressure terrain, they contain so-called C defect, okay, and A defect, but they do not contain B defect. So they belong to group AB1AA, so which characterize a very low nitrogen aggregation. What does it mean? It means that this diamond did not have a long residence time inside of the Earth in that depth where diamond was formed. We also study from this research that nitrogen contained in this diamond is about 160 to 1,633 ppm. So let's now summarize this result and see how this diamond can be compatible or different from kimberlitic diamond. For that, we go to a famous diagram created by Cartini and published in many other papers. We see here nitrogen aggregation, okay, from 1B, small b, and 1AA, and 1AB. 1AB, this is mostly kimberlitic diamonds, okay? And you see the field of the diamonds from ultra-high pressure terrain. The red stars, that's data from these two diamonds, which I demonstrated in the previous slides. So what we learned, what we see here, the diamond from ultra-high pressure terrain, they have a high nitrogen aggregation, higher than, in general, diamonds from kimberlitic pipes, okay? And also they belong to type 1B, 1AA, but kimberlitic diamond, mostly 1AA, 1AB. So it's a very good discrimination. Then we prefer to work with the same sample, because you know, when you go from one facilities to other facilities and you bring different samples, even from the same rock, you can get some conflicting data. So new technology came, and we started to use in that time ComPetro-AGA nanosims. What does it mean, nanosims? Everybody knows sims, okay? However, nanosims has a very, very tiny beam, 50 nanometers in diameter. It means that this beam can penetrate very thin sample. It means that you can go to nanosims instrument to study carbon isotopes with foil, which you prepare for transmission electron microscopy. So we did this in collaboration with the University of Tokyo. In that time, that was one of 3 nanosims available in all universe. It was the beginning of this era. So nanosims is a nanosecondary ion mass spectrometry. And it came to replace traditional method, combustion. Yeah, you make a combustion of the mineral, and then you have the carbon in this combustion product, and then you measure isotope. But here we have opportunity to put your thin section with your diamond, with your small inclusions inside, and study in details from place to place carbon isotopes to understand homogeneity of the carbon isotopes. So delta 13 ratio to delta 12 is the main characteristic which known as a delta 13 carbon isotopes in diamond. So this is how laboratory looks like. It's a complicated instrument, but you learn it by yourself. You participate in all this setup, and the operator and other people who are responsible for this instrument, they bring you a lot of technical knowledge, and you as a user of this instrument have to learn that, to understand the data which you receive from them. So let's see now, you take this thin section, okay? This thin section was polished. You see here, garnet, garnet, garnet. And this is a red triangle show diamonds, which were found in each of these garnet. So we go with this sample first to nanosims. Nanosims has a cesium beam diameter, 50 nanometers as the cell. And you see here carbon 13 mapping. You see here different intensity of the color. It shows how intense is carbon 13 in this particular diamond crystals, okay? So you see here this part of the elemental mapping we put on this diamond and exactly show the area where the delta 13 distribution show us the intensity of these parameters. So, okay, now we summarize this data. And I show you, for example, this is a garnet, one crystal, where we found several diamonds. This diamond, this diamond, this diamond, okay? We show this diamond here in high magnification. So we can see that in, this is the bar scale, 3 micron, this bar scale of this garnet, 4 millimeters, okay? This is part of the same garnet magnified. So what we found, we summarize the data. We found also that the garnet has a chemical zoning, okay? So the chemical zoning show that different magnesium compound in the core, and then zone 1 and zone 2. So we decided to look if the diamond, which is sitting in zone 1, okay, and diamond which is sitting in zone 1 and in zone 2 have similar carbon isotopes, okay. The data show, when we summarize everything, that zone number 1 contained diamond with delta 13 minus 17.8 and nitrogen 820 ppm. But diamond, which is situated in the outer zone, okay, zone number 2, has a minus 23 delta 13. It's a heavier carbon, okay. It says that we are close to the more shallow level. So, and nitrogen is almost twice higher. It's 1,838 ppm. So probably we have some fluid rich in nitrogen and carbon, more intense fluid, which is in the shallow depths of diamond crystallization. So now we would like to see again how these parameters, nitrogen content versus to delta 13, compatible with the kimberlitic and lamproitic diamond. We have the same diagram of Cartini plotted our data. This is diamonds from Cockchetov Massif, okay, a diamonds from Erzgebirge Massif. This is kimberlitic diamond. We see that they belong to different fields. So the ratio of nitrogen to delta 13 definitely different. And you see that delta 13 is from minus 10 to minus 30. It's characteristic of the ultra-high pressure terrain diamond. The diamond from kimberlite mostly consists of the heavier carbon. So now this is the diagram which shows carbon isotope characteristic for more oceanic island basalts, carbonates from kimberlite, carbonatite, diamonds from mantle xenoliths, and organic meta and archean carbonatite. What we see here diamonds from ultra-high pressure terrain, Erzgebirge diamonds from Germany. They are characteristic of delta 13 carbon, minus 17 to minus 30, okay? And Cockchetov Massif, a little bit heavier, but still from minus 10 to minus 17. So this allows us to conclude that this diamond, delta 13, provide evidence that this diamond crystallized from a crustal carbon, light carbon. So now we want to study nanoscale inclusions in this diamond. We study this with the instrument focus ion beam. Focus ion beam, it's a new instrument which actually was developed by a Japanese company at the beginning, and then Fei company in the United States. And it was built up to study failure of small devices in computer devices, computer plates. Because, for example, if you have a lot of computers, okay, and the computers fail, you have to find what happened. You go to look their semiconductors, and they are very tiny, and you have to cut them off to look on the microscope. So the focus ion beam instrument was triggered by the demand of the computer industry. IBM computer industry supported the development of this instrument at that time. So what FIB? FIB is just like an electron microscope. Yeah, this is the same setup. There is a vacuum chamber inside where sample is going, and there is a scanning electron microscope which is combined together with this focus ion beam. But the focus ion beam consists of the ion beam of gallium. Why gallium ions? Because gallium is very dense and creates so dense beam which can cut, or we call this mill out, milling process, mill out diamond. So this is how this technique looks like. You have a polished thin section with a mineral of your interest. You first look at optic microscope. you choose that area which is a great interest for your research, okay? So then you bring to scanning electron microscope, and then you put two crosses where you will study your material. It's some line, you know, when you come to focus ion beam, you already have this mark. You find this place very easy. Then fib milling will start above and below of this marked line, okay, this step 2. Then focus ion beam foil will be prepared. You see here, finally, you have the plate, very, very thin. It's 10 by 5 microns, but thickness is 50 to 100 angstrom. It should be very, very thin to be transparent for transmission electron microscopy. So this is, you see the details of the diamond. This is again polished zircons. Again, you see diamond. You found diamond of your interest. So you polish very well. This is how diamond look like. You made the mark. You want to cut this diamond along this direction. So then you have to coat this diamond with the nickel, because the ion beam is very strong energy beam. It can damage diamond, destroy molecule of carbon. To protect from this damage, you coat with nickel. So then the milling started. And you see here, this is the big trench, another trench you don't see from here, but this is our foil, okay? And this is diamond. And this is finally another diamond, even here, standing out from this foil. This is covered by nickel, why it keep the sample intact. So from both sides, you have to cut this plate. And there is a special excavation technique to pick up this diamond from the vacuum chamber and place to another instrument, which we call transmission electron microscope. This is under high magnification, 5,000 micron, how this foil looks like on the transmission electron microscope. So you see here inclusions, right? We observe in this particular foil 3 inclusions. We also observe very well grain boundary, the boundary between diamond and host mineral. You know that this diamond sitting, for example, in garnet, okay? But you see here, direct contact between diamond. You can study interface, the atomic setup between diamond and garnet, how they attach it to each other. This is the history of growth of diamond. Then you find here chloride between garnet and diamond. It can be secondary chloride. However, it was known from experiments that chloride is stable up to 5 GPa. It can be formed in the diamond stability field as well. So again, you see chloride between garnet and diamond. So a lot of information, you can get it. Now you see what we can see in this foil, what we get from that, okay? So we confirm the temperature and pressure and depth of crystallization of this diamond. When we went to that carbonate inclusion, you see here, we found that that carbonate inclusion consists of 2 sets of inclusion. You see bar scale, 60 nanometers. We found there calcium CO3 with aragonite structure. It's not calcite, it's a high pressure form of calcite with aragonite structure. We also found magnesium CO3, which is magnesite. We know that there is a breakdown reaction of which produce calcium CO3 aragonite and magnesite from calcium MgCO3 too. Okay, so when we know all this data from TEM studies, then we go to search experimental setup. And we found a lot of data, experimental data, which show the pressure temperature phase diagram of breakdown reaction of calcium magnesium CO3 with production of aragonite and magnesite. So we determined that for this particular diamond, the crystallization pressure was between 7.5 to 9 GPa, and temperature was 1,250 to 1,500 K. So these conditions correspond to depth about 200 to 180 kilometers. So we learn a lot about this diamond. Then we want to learn how diamond was crystallized. Okay, was it in a solid condition, conversion of some graphite or some amorphous carbon to diamond, or maybe melt or fluid was involved. So our observation at optic microscope and SEM show that sometimes these diamond inclusions they are multiple. They just consist of different group of minerals which create so-called pocket. Okay, we call them former melt pocket or fluid pocket. For example, here you see 10 micron bar scale. So this inclusion in garnet, okay, it contains many minerals, okay, and the size of this inclusion 20 to 30 microns. What we see here, we have one diamond crystal, another diamond crystal. We see biotite, we see quartz, we see graphite, and we see phengite. So we have this isolated pocket, 1, 2, 3, 4, 5 minerals together. So we believe that they were crystallized from melt or from the fluid. So we understand now that these minerals are not in equilibrium with diamond, biotite, quartz, graphite. In this particular pocket inclusion, we have albite, diamond, phengite, and SiO2, which is now quartz. So we want to find the bulk chemistry of this inclusion, what this inclusion was before crystallization of these minerals. And we understand that there were two stages of this crystallization. First, ultra high pressure, where we had diamond, probably coesite, okay? That was probably during subduction to the diamond stability field. And then when rock were moved back by the exhumation process, we have conversion of some ultra high pressure mineral to low pressure minerals, like biotite, quartz, and phengite, graphite, so albite. So we can study this process separately. And we did that because technique help us to do that. This is focus IL beam foil prepared. At microscope. We look at inside of diamond and we found first this platelet. We know it's a structural defect of carbon atom. Then we see suddenly this round material. Wow. And we looked at this round material. And finally, we see this round material started to move. Here, you have to start to think very fast. What does it mean? Because you see, it's probably bubble of gas or fluid, okay? And also you see here, during the movement, you see here the crack, and you see here the contrast became very bright, white. What does it mean? It means that this inclusion will be perforated very soon, okay? Because we have high energy beam, and it will burn this inclusion. And it happened. You see here, we have the hole. This is bright material, bright white material. Is a hole. The foil was perforated. We lost fluid inclusion. However, if you look at here, how fast it happened, the beginning when we started to study was 10:45 a.m. and when inclusion disappeared was 10:51. It took like 6 minutes to act because we had a very good guess that this is fluid inclusion. It was a very exciting moment and very new for us as well. So we had a chance to measure composition when inclusion was alive. And we found with the EDS spectrometer, which is available in transmission electron microscope, that there is calcium, there is a potassium, there is a iron, there is a chlorine and sulfur and oxygen and the carbon, of course, in this fluid. But when the fluid was perforated, we know this happened in a vacuum chamber. The part of the material precipitated around, but we don't have a volatile materials because they're gone. So really, when we measured material around, we found that there is a calcium, there is a potassium, okay, you see these peaks, still there is an iron, but less oxygen. We don't see any chlorine and any sulfur left. So we understand now the fluid composition. Then another example of the inclusion which was surrounded by fluid is the aragonite, okay? And you see here the contrast, which is very bright. It's already cavity. You already have foil where fluid was perforated, maybe by focus ion beam when foil was prepared. So we would like to conclude that this sample was a unique exemplar which was available for us probably by chance, because this happened not very often. Fluid can be perforated very easily. So then we study another material. We study diamond inclusion in graphite, and we just also found a lot of fluid here, and we were able to discriminate this fluid inside of diamond. We also found chlorine, sulfur, silica, aluminum, calcium, and again, focus ion beam helped us. Then we study polycrystalline diamonds, which we discovered again within zircon. This is a foil was prepared. You see here 12 crystals inside of this polycrystalline setup. We also found fluid pockets here and measured their composition. So make a summary on that. Again, you see here fluid pockets. Here already perforated, but here fluid still alive. So we measured them and then combined all data. We plotted them on the diagram of the triangle diagram of hydrous, silicic, hydrous, saline, and carbonatitic fluid, which was developed by scientists who study fluid in diamonds from kimberlite and in experiments. The curve 1, 2, 3 experimental curve, which show the evolution of the fluid in experimental diamond, which made from fluid in experiments. And this is on the fluid, the red line, it's a fluid evolution in diamonds from kimberlite. When we plotted our data, we see that diamonds from Kazakhstan and Erzgebirge, they contain fragments of hydrous silicic fluid, they contain fragments of hydrous saline fluid, and they contain fragments of carbonatitic fluid. But carbonatitic fluid was found only in Kazakhstan, metacarbonate rocks. We don't have metacarbonate rocks in Erzgebirge. So why their fluid a little bit different than in Kazakhstan diamonds? We don't have carbonatitic fluid, but we have hydrous silicic and hydrous saline fluid. So this data now should be summarized. What did we learn from study of fluid inclusion and carbon isotopes? Yes, the summary says that the study concluded that low density fluid rich in carbon organic matter can migrate very deep during subduction of the material, at least to depths 200, 280 kilometers, where it is precipitated in the form of diamond. So then we started to study noble gas isotopes. Noble gas were detected in these diamonds, helium-3, helium-4, neon-3 isotopes, 20, 21, and 22. We started to study with Japanese scientists from the University of Tokyo. And when we studied this neon gases isotopes, we found first that they are plotted on the diagram with the oceanic island basalts hotspot. So oceanic island basalts are made by mantle plume. So this another data, neon-3 isotopes, neon 20, 21, 22. This is our data. And this is magnification of this data. You see this green spots, it's our data from diamonds. They plotted on the field of the neon isotopes, which characterize Hawaii, Iceland, and Galapagos. It's an oceanic island material. So we prove that diamonds from ultra-high pressure terrain was interacted with the mantle plume. Of course, how it happened, we don't know exactly. We can hypothesize that it happened during a large scale mantle convection. Some deep mantle fragments were brought to the mantle transition zone where diamond from ultra-high pressure terrain can be formed. So also it met with the material subducted together with continental crust, some fluid, some organic carbon. So in a mixture, interaction of this material created this unusual combination of the noble gas isotopes. So what did we learn from noble gas? What is a big concept? Subducted slab interacted with deep mantle plume. Subducted slab maybe was contaminated with the mantle fluid through the interaction with mantle wedge containing fragments of very deep mantle. So this is the end of my talk. I would like to acknowledge the United States National Science Foundation, which provided several grants to study these diamonds. When we found the appropriate technologies to show that this is real diamond, then Pacific Rim Program, organized by University of California, Los Alamos National Laboratory, Consortium for Materials Property Research in Earth Sciences, Japanese Society for Promotion of Science, and Helmholtz Center in Potsdam, Germany. So thank you very much, and I would like to take your questions now.
Bueno, le doy las gracias entonces a Larissa por su hermosa charla y le doy lugar a los que quieran hacer preguntas a Larissa. Si hay alguien que tiene preguntas, por favor active su micrófono y su cámara, así podemos escucharlos. Vamos a dar lugar primero a las personas que están conectadas por Zoom. Si alguien tiene alguna pregunta para hacerle a Larissa o quiere hacerle algún comentario, le damos lugar entonces a quienes quieran hacerlo.
Florencia, if they don't have questions right now, okay, then they may address these questions later via email to you, then you summarize, and I can organize Zoom individually for people who has interest. We can talk with them. Yeah, I'm just available to share all my experience and all data. And I want the Mineralogical Society of Argentina to spread interest to this diamond and find diamond in your country. Yeah. That's what we are both for moving ahead the petrological and petrographic research.
So thank you very much, Larissa, for giving us this talk and for sharing with us your knowledge. And we hope that somebody wants to ask something. So here we have a question. Can you see it, Larissa, in your screen?
Yes, I see. Thank you very much for talk. For very clear, interesting, wonderful research. Okay, it's not a question, it's just a question. Okay,
just a
okay. Okay. Yes. Thank you.
So let's see if there is a question in the YouTube channel. So let me check. If we have so no, we don't have any question here. But like Larissa says, if someone have a question and want to write her, I will give to you my email, so then you can send the question to me and I will send the question to Larissa.
Okay.
So if there is no questions, I would like to thank you very much, Larissa, for your lecture. It was very, very wonderful. And in the name of the ComPetro and the Geological Association of Argentina, I thank you, and I hope you have enjoyed this time with us.
Yes, I do, and looking forward to collaborate with you when pandemic will be over.
Yeah, of course. We hope so.
Okay, so thank you.
So,
We'll finish, right?
Yeah,
hay un saludo de último momento en YouTube de Mercedes Agostinelli que dice espectacular. Thank you, Larissa, for your time.
Oh, thank you, Sylvia. Thank you very much. I'm sorry that I cannot speak Spanish, okay?
Okay.
Okay.
So,
Bueno.
Larissa, then, les agradecemos a todos los presentes por haberse tomado un tiempo de escuchar a la charla de Larissa y a los que se conectaron por Zoom. Les agradecemos a todos y bueno, esperamos poder tener...
I make a photograph, okay?
Esperamos poder tener a Larissa como invitada en alguna otra oportunidad o en algún otro evento que organicemos en Argentina.
Okay.
Muchísimas gracias.
Yeah. So then goodbye.